So let's start with where we were. So I started to do facility location, but I'll go back a little bit and I'll start with weighted set cover. Okay. So if you recall weighted set cover, what we had is like universe and a family of sets, and there was a weight on f to r positive. Okay, and our objective was to cover f prime subset of f with minimum cost or weight, whatever you want to call it, right. So there was a cost function or weight function. So you wanted to find f prime subset of f with minimum cost that covers u, right. So that was an algorithm, that was a problem. So if you recall correctly, the algorithm was very fairly simple. Okay. So basically we started with initially covered was an empty set, right, and what did we see? While and C was C and U was U, while u is not equal to phi, in the beginning I have substituted u, right, find a set, or you don't even need, okay, or rather you also don't need this, okay, while C equal to u, right, while C is not equal to, I do find a set x, okay, find a set x in your family, okay, with what are the cost, okay, find a set x in fam where per, okay, so weight of x remains, but its cost is how much is left to be covered, okay, which is like basically, or I think best is to keep u, okay. Okay, so currently what is the current u intersection x is, right, find a set such that what u intersection u is in the beginning u, I will so u is not covered, I will update, I have not written anything, right, right, find a set x in f such that this is minimized, right, minimized, and then I would do what C union x, and u is C is C union x, u is u minus x, that is it. So I have updated it. So every time this u contains uncovered element, okay, uncovered elements, and this contains covered elements, okay. Now if you notice, so this is u, yeah, or in the while u is not phi, doesn't matter, okay, okay, but that's not what, tell me what is your question, Karthika? U is u minus x. X is a new set of elements I covered. So now what is the current set of covering requirements is u, right? You already covered x. So now the remaining set of elements that you need to cover is u, right? And I added x to C because C is like a covered. So this is like, okay, whatever, okay. But that is not what I was trying to do, okay. So notice that so this is the algorithm that we did, okay, and there were several analyses we did, but one analysis which was particularly interesting and it was important was what I call charging scheme. Okay. Okay. So what was the charging scheme? Notice that at any point of time I have added a set x, right? I have added a set x. So suppose I added a set x1, x2, x3, xl. So L sets that I added at any point of time, okay, okay. Madhumita, there is no point watching backwards, it is not helpful, okay. So we added sets x1 to xl, okay. Now when you, so if you added x1, what, yeah, in this order, okay. So how much did I pay? Weight of x1, right? How much did I pay here? Weight of x2. How much did I pay here? Weight of x3. So this is what algorithm paid. This is what algorithm paid, okay. But notice in the first step, actually what element did I cover? Some x1 elements I covered. In the second time, I may not have covered x1 elements, but I only covered those elements of x2 which were not already covered. Okay. So let's call that x2 prime. Like, what is this? New set of elements of x2 that are newly covered. Right? You understand the point? Right? Okay. X prime. Right? So this is what happens. Now, what is this tells us is that, okay, whatever maybe the cost of x1 is, let me distribute whatever the weight of x1 is, let me distribute over its weight to the elements that it is going to cover. You understand? Okay. So now so look at the set of elements that are covered here. Okay. So now this is what I say. Okay, every element that x1 covers. Okay. So these are the elements that x1 has covered. Okay. What is its each of the weight is? What did I said? Each of its weight is weight of x1 divided by u intersection x, which is cardinality of x1. So I said, what was alpha 1? Alpha 1 was basically weight of x1 divided by x1. Is that fine? Okay. So now if I sum alpha 1, alpha 1, alpha 1, alpha 1, what is the total sum? Is weight of x1. So this is fine. So now I have think of this way, that this weight of x1 is distributed over all these numbers. Okay? Okay. But this number is still each of them is get alpha x. So their total contribution here is still weight of x1. Now look at the newly x2. What happens to x2? Okay? x2 will be some new set of elements are added, some new set of elements are added, and what is alpha 2? Is still weight of x2, but I divide by size of x2 prime, not x2, right? Right? And this is what is alpha 2, alpha 2, alpha 2, alpha 2. So how much did he cover? Still the total weight is weight of x2. Why? Think. Wait. Think. It's written there, no? Madhumita, it's my class. Tell me why the sum of this is not equal to weight of x2.
Because we are choosing for x2 prime, right?
What is? So what is the definition of alpha 2?
Weight divided by x2.
How many elements are here? So if I divide x, multiply with this, will I not get weight of x2? Okay. And similarly, this is what is happening. Okay. Similarly, everywhere is happening. Okay. So now notice what is my greedy algorithm tells. Okay, fine. So rather than counting the weights of sets, I said let's every element get something. So what did I do? I said every element gets a number. Okay. And okay, every element gets a number. Okay, gets a number. Okay, like how? So this is how you give them number. So these elements got number alpha 1. These elements got number alpha 2. Okay, but so now let's suppose if my elements are 1 to n, I'm going to call them their number is equal to alpha I. Their number is equal to some alpha I. Okay. But okay, some alpha I is their number. Now if I summation do over alpha I going from 1 to n, what is this equal to? If I sum their numbers individually, what will I get? Cost of the sets that I picked. That's it. Okay, why it is useful? Now I can think about each element, right? So every element says, look, when this algorithm picked me, this is what I paid. For picking me, this is what are the payment I paid. Okay, so for every element, I have associated some number alpha I. Okay, so alpha I could be equal to some of these, or let's say not alpha I. Let's say every gets beta I. Okay, beta I, and what is beta I? If you are here, it is equal to alpha 1. If it is here, it is equal to beta 2. It depends, you understand? If the ith element is picked here in the ith round, then his weight is equal to. So, I am saying if ith element is picked by some jth set, okay, then what is beta of I is equal to some alpha j, right. So, if I am picked up by this set, then if, right, so this is what it is. But now if you sum over beta i's, I going from 1 to n, it is equal to summation over weight xi, I going from 1 to L. Is that fine? Is everybody okay with it? Why am I doing this? Okay, what is the objective of doing this way of doing these things are? Okay, so this is just, so what it tells me that look, what I am trying to tell now is look, every vertex or every element, when it is covered, it pays some amount of money. Okay, and if I sum their total money, then is the total payment done for this set cover. Okay, now why it is useful? Because look, any optimum solution also, look at any optimum solution, say O1, O2, OQ. This is my optimum solution. Doesn't matter in which order you go. O1 picks some set of elements, right? O2 picks some set of elements which O1 does not. Maybe they pick. So this is like, so I'm going to write down this is O1 in some order. This is O2 prime, O2 prime, OQ prime, right? Okay, you understood what I'm saying, right? So these guys also covers all the elements. Okay, now if I had approved a lemma that look at any set, this is where it could be, look at any set in your set cover, any set in your family, any set, huh? O1, like look, O2 can have intersection with O1, no? Okay. So let's suppose that I go in this direction, then a newly set of elements covered. Okay. But look at any set S, okay, in my family, or look at any set F in my family, any set F in family, and I say, hey, F, look at summation of beta I in F. Look at those elements which are present in F, right? How bad is this? How bad is this number? I put up a set and say, look, it contains some set of elements and every element has some number. So if I would have picked this set in my solution, then I would have probably paid these numbers. You understood? You understand or not?
I have paid these numbers.
No. That is, I have picked up x1 to xn. Yes?
Can you please repeat whatever you said?
I didn't get what you're saying.
Sir, I am asking, can you please repeat?
Oh, repeat. So what I'm saying to you, look at any set F, look, my algorithm, I have told you, given an algorithm procedure to define betas. Is that fine? Okay. Now I forget about anything else. I want to understand that I fix any set, not necessarily an optimum solution, not necessarily picked up my May. Okay, I want to understand any set F in family. Okay, what is its weight? Is weight of F is weight of F. Okay, and F contains some elements, right? Some elements. F contains some elements. Okay, F contains some set of elements. Okay, now if they contain some element, then they have some beta values by definition. I want to understand if I sum these beta values. Okay, look at this summation beta I going from F. This is some number and weight of F is some number. How are they compared to each other? How bad they are to each other? Okay, so if I can show that, look at here, if I can show here summation beta I in F is less than equal to 33 times weight of F. Suppose I am able to show this. What does it imply? if I'm able to show that if I sum these guys for any set, okay, their summation is upper bounded by some 33 times weight of f. What is the meaning of this? What can I achieve if I prove such a lemma, right? What is an objective if I prove some lemma? What is that? How is weight of any set related to cost of charges, right? So what is this? This lemma is best tells us relation between weight of a set and cost of sum of charges of elements contained in it. Okay, that's it. That's a relation. Why am I doing this? If I did whatever I will prove here, I can show you something interesting. Okay, how? Okay, look at. So you have understood this. You have believed me that this is summation of beta is summation of this. Okay. Now let's try to understand here. Okay. 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 So now let's just concentrate. Speak. Let's speak slowly and let's concentrate. Okay. Okay. I want to understand what is summation of beta i's r, right? What is summation of beta i's r? Okay, what is this is what I'm interested in, right? Because if I want to have an understanding of this, I better understand this. Okay, but now I want to understand. Look, let's forget about any set covers. I know that my universe is also covered by my optimum set. Okay, so O1 covers something, O2 covers something, OL covers something. Do you agree? But their union is U. Is that fine? Okay. Then I say this is less than equal to, because it is about covering, this quantity is less than equal to I going from 1 to L summation. Okay. Summation beta j. Is this fine? Look at left hand side. Every element is in some of the sets because these are covering, and this is true about any covering that I could have written this upper bound. For any set of objects that covers this, I could have written this side. You understand or not understand? Look at this. Look at A1. It covers some set of elements, no? So those elements betas are counted. O2 might cover some other elements and maybe some before. Again those are counted here. Doesn't matter, but is it not counted? It is counted. This, if this element appears in all the L sets, it is going to be counted in all the L sets. Look at the summation. What did I say? Look at the sum. It's over counting, but doesn't matter, right? What I want to say that any element which is every beta 1 is at least present once here, and that is true because every element is covered by some set, and it has nothing to do with this O1 to OL. If I would have come up with any covering of my universe, I would have been written this right hand side. So in particular, I can write this for. Okay, fine. What does this lemma tells you? What does this lemma tells you? Hey, for any set, sum of the charges there is related to its weight. By how much? By 33. What does it imply? This will imply that what is this quantity is less than equal to I equal to L, sorry, summation I equal to 1 to L. What is this? 33 times weight of Y. Is that fine? Which is 33 times summation I equal to 1 to L weight of Y. Okay. Now, what is weight of Y? We started with an optimum solution. So this is 33 times opt, right? So the moment, so what is the property of charging? Charging allows Charging allows us to argue about elements to sets. Key lemma that any set and their charges are related by some factor. So, if this is not have been 33, if it would have been some capital delta, then this would have led to capital delta and capital delta. Okay. So, strategy for most greedy algorithms will remain the same. The difficulty lies in proving this lemma. This will be the key to the, but everything else is just a generic steps. So, when you are thinking about these kind of algorithms, all you have to say, hey, how is the sum of my charges is related to the weight of my set. You understand, right? Whether you can prove or not prove is a different thing, but algorithms analysis is not going to change. Okay, whatever I am going to charge the cost, I am going to, so whatever may be the total cost of my sets, I will find a weight function which assigns weights to each element. If I sum the weights of each element, that is equal to what I wanted, and now locally I will try to understand these things with respect to this function. So, that is an overall scheme of doing things. Okay. We can replicate it for any problem, okay. Be it k median, be it k mean, anything where there is a covering constraint, we can do this. Okay. There are several ways of proving this. People prove this using greedy, people prove this using primal dual, people prove this using local search, but this is what they prove at the end, that my charges, my weight. So, charges can be defined also in several ways. Greedy will define this way, LP will define by LP values, SDP will define by SDP values, but this is how it is defined. Okay. Rounding will define by the rounded value, you understand, but most algorithm will need to show using some charging scheme if you are trying to apply has to show such a crucial lemma, that the charges which I defined and my weight of the set, they are correlated to each other. Okay. Now, why did I do this? Because when I do facility location, neither sets are obvious, not set coverage obvious. Okay. Then what are you trying to do? Right. Now, you understand the lemmas they prove, because implicitly they are proving exactly what this it is, right, which of course they will never write. Okay. Okay. So, that was a precursor to what I wanted to tell you. Okay. So, what we were able to show that this is equal to log of size of f. So, for set cover we showed that delta is equal to log f. So, in fact, we could have proved this lemma, there is nothing here, right. This for any problem, if I have such a scheme, if I prove such a lemma, I have such a theorem. Is that fine? Okay. 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 So, that was about weighted set cover. Okay. Now, we will go back to facility location and try to see what are my sets, what is my greedy approximation, what are we trying to prove. You understand? And then of course, there will be a lemma which I do not understand, but that is okay. Any question? Online, any question?
No, sir.
Okay. Okay, so let me write down the, and if you want me to slow down, you have to tell me. Don't expect that I will slow down like my own. Okay, so we are talking about UFL, uncapacitated facility location. Okay, so what are we given? We are given a set F. This is set of facilities at some location that it can be opened, okay, and C is set of clients that we want to serve, okay, and there is a distance function okay. There is a distance function from facility to a client which is say r greater than equal to 0 okay, which tells us that if what does this tells us, if a client, what is the DIC equal to alpha will mean? It means if a client C is served by facility I, then he will have to pay some alpha okay. So this, so what is given? Facility is given, cost is given, a distance function is given okay. And okay, what is my output? Output is x subset of f, meaning these are the places where I am going to open my facility, and a function sigma which maps client to x. What it tells? Hey, this client is served by x, and a function which tells me that which client is served by which facility okay. Okay, and sigma c to x is like to nearest facility okay. So basically look at a client, look at the different that facility comma c numbers, and you assign it to the nearest facility okay. So every client is assigned to nearest facility okay in x. Is that fine? And that is good. And but what do I want to optimize? I want to optimize certain cost function. So what is my want to optimize? And cost of x, what is the cost of x? First of all, I open certain facility in x. So I in x facility of opening, and now there is a cost of serving okay. So what is the cost of serving? J in C okay. This function, is that fine? Right. So I want to output x such that cost of x is minimized okay. And at this point of time I am not assuming anything about d okay. So it does not look like a priori that it is a set cover problem first of all right. A priori it does not even look like the set cover problem, but there are sets and there are covering okay. So first of all so there are something which I am going to cover okay. So what is this? My universe is my set of clients okay. Now a priori I have no idea right whom I am going to, what are my sets right. So sets are basically, how will you define a sets? Basically if I have a facility and look at the set of clients it serves, this is some facility serves some C prime subset of C right. So this could have been a potential set, but neither do I know I nor do I know which C prime that it can. That I have a priori no idea, it is not given in the problem right. It is not given in the problem, but potentially when I talk about covering I could have this C prime could potentially act as a set of elements that are covered, and how, who covers it? A facility opened at I, which implies that potentially here are my potential facility location facility. So what is my family? My family is going to consist of I C prime okay. I is in F and C prime is a subset of C. This is my first right. I do not know which one, but like any potential sets that could have been used for covering is written here. What does this mean? What is this I C prime set means? Hey, or like I should not write this okay. This should be right F I C prime. What is F I C prime? F I C prime is equal to C prime, but its name is I C prime, which tells me that hey, when I pick this set I am served by set I, facility I. My universe is C, my family has to be subsets of C.
What is the F function?
Function is a name of the set family. I, like imagine, like I is in the this, what is FIC prime? Where is F? Okay, fine. Okay, so this is, let's call this F I C prime. Okay, and what is F I C prime is nothing but set of elements in C prime. That's it. But I call it my name I C prime, just to mean that whenever I pick this set, it is I who will be serving them. You understand? For every C prime subset of C, this family has. So what is the size of this family? It is size of F times 2 times size of C. Okay? Okay. So this is what it is. Okay? Okay. Now weights are very clear, right? If this is the guy who is going to serve me, how much weight he should have, right? How much weight should he put? His weight, his or cost will be how much? So first of all, if I picked up this set to cover, it means first I opened up a facility at I. So if this is going to be Fi plus all this j in C prime is being served by whom? I, right? So distance from I comma j. So this is the cost, or this is the weight function, however you want to call it, right? This is what it is. Okay. So now, okay, now this family is extremely big, but at least we have what families it is, what this, but does it actually correspond to the problem that I am interested in? You understand what I am saying? I wrote it like this. Does it mean that if I find a optimum solution here, that corresponds to a solution here, and that, you understand my point, right? So I want to say, I want to prove the following lemma. Okay, what I want to prove the following lemma is that if x rho of cost, if x rho has is a solution, x rho, x is given to me and rho is given to me. If x rho is a solution, then we have corresponding f prime subset of f of cost at most L. If x rho is a solution of cost L, then weight at most L. That's the first lemma. That if you give me any solution here of some weight, I can translate it to a set cover solution of same weight. Okay, how? That's very simple. Okay, how do I do this? Okay, how do I do this? This is very simple, fairly simple. Is that okay? You are given me x subset of f, and you are given me rho from C to x. Okay, rho to C to x. Okay, now okay, for all I in x, okay, what is Ci? Is all those Ci is basically sigma inverse of I, all those elements in clients who maps to the facility I. You understand? So if I draw a picture, I have opened some facility, okay, and every client by map sigma is assigned to some people, and it's a partition, right? So now I am saying, okay, fine, if this is a client, if this is a facility that serves these guys, let me go to the corresponding Fi, see here. So Ci is this. So now what are the sets I will take? I will take Fi Ci in my family for here, right? Given this solution, consider F I C I in X, as a cover for U. First of all, does it covers every client? Yes, my universe is all the clients, and union of Ci is basically equal to U. So it is a covering. Are you okay, or are you confused? Okay. Okay. So this is what happens here. Okay. Now what is its cost? What is its weight? It's basically, its weight is going to be weight of Fi Ci I going from I in X. But what is weight of Fi Ci? What is weight of Fi Ci is Fi I in X summation j in Ci dij, right? But that is exactly equal to cost of X is, which is at most L. So this is done. This is same as cost of X, and this is a definition of cost of X. Okay. So if you give me a solution here, I can give you a solution of the same cost here. Okay. Now we need to prove the thing in the reverse direction, that if you give me solution to this problem, I can give you a solution to my original problem. Is that fine? Okay. Okay. So I need to prove a lemma analog of this. So what is the lemma will be? If f prime subset of f is a cover of U of cost L, then there exists x comma sigma, then there exists x comma sigma of cost, let us say of weight at most L, then there exists of cost at most L, right. So if you give me a family f prime of which is a covering of U and whose weight is at most L, then I will give you an x and rho here whose cost will be at most L. Is that fine? Okay. Okay. So how do I do this? This is fairly simple all over again. Okay. Okay. So now look at your f prime, which is subset of f, right, and it is going to consist of some sets, right, some sets it is going to consist of whose weight is at most L. Is that fine? Whose weight is at most L. Now I try to see, but now I group these sets based on what I. So for example, look at this. It's possible that I have f I C A, I have another set f I C B, I have another set f I C L or something. Like I could have several sets corresponding to the same facility, like f I, because this is just a set cover instance, right. So you have given me some set family. Yes or no? Do you understand that in this f prime there could be several sets there, the first index is I, because it's just a set cover. What is my goal? Give me some subfamily which covers all this. Does it going to bother what is I? And this is just some sets for him. Okay. But then if I have same indexed I, okay, then I'm going to group them together. How? But I know that I have a following set. Okay. What is the following set? I will add f I C A union C B dot 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 union C L. This set is also there, no? Because it is for all C prime subset of C. And what is the cost of this? What is the cost of this? What is the cost of this? This is the cost of this is less than, is equal to f I plus summation everybody assigns to I. But look at f I C I. it Fi plus assignment, FICB, Fi plus assignment, Fi plus some assignment. So if I replace these sets and add this set here, what I have? I still cover everything and its cost is maybe smaller. Imagine if you have F1 CA, F1 CB, what is its cost? F1 plus summation di, okay, sorry, D1, right, J in CA, is that fine? Plus F2 plus summation J prime in CB D1 comma J prime, is that fine? Now if you replace them, definitely this cost will go away, right, because you will only add for this particular set once, right. So if I do F1 Fi, so what it will be? So it is going to be Fi plus summation J in this CA union this distance I comma j, right, is that fine? Now it is union, means each of element will appear somewhere here. It's possible that same element might appear several sets, then I would have counted this, but definitely by adding this set and removing this, I have not increased the cost, I have only decreased the cost, right. So I will delete FICA, FICB, FICL and add this set to my family F prime, F new, I made new F double prime, and I keep doing this. What is the property after this? After I have done all this step, for each I there is only one set here. Is that okay, or are you still confused? I mean, if you don't understand, learn to ask question, Madhumita. Making faces doesn't help. I'm just repeating what I have taught before. You have not gone and looked at, many of you have not even bothered to go and look in the courses. I understand that much. And then you think that you will become a genius one day, not going to happen. And this is the case with almost every courses. None of you people go in and follow up on the courses. I understand that much. Okay. So I will keep doing this, and at the end what I achieve. Okay. So if I do this replacement, okay, I will get some F hat subset F hat, new F hat, and what is the property of new hat? For each I in facility, there exists at most one set in F tilde. Is that fine? Okay, 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 fine. But now given this F tilde, I still need to define something. Okay. So how will I define now? I'll define as follows. Okay, okay. So look at, I have to define a sigma, and I have to define client to look at what is, okay. So let x be subset of F for which there is at least there is a set in F tilde. So for each facility I, if it contains one set, I add that index to X, for which there is a set in F tilde. What is my X subset of facility? For which there is at least one I for which there is a set here. If some I does not exist here, I don't care. You understand? Every set was defined by index from facility and a subset of my this. What was this? F I C prime, I in my facility, C prime subset of C. So if I am telling you in F tilde, if some I exist here, then I put that into X. But there is possibility that some I in F does not exist at all, then I don't put in X. So I have defined what my X means. Now I have to define a function from C to X. How do I define? This is very simple. Okay. How do I define? I mean, how can I define this? How? Or do we need to more clean up operation? Not required, but you can do it. Okay. So you start. Okay. So suppose these are the sets here. Okay. There is some sets here, right? Some sets here, some sets here, some sets here, some sets here are here, right? So first, just arbitrarily put them in a order. All this guy gets assigned to whichever I he is. Okay. Next, those who are still left to be covered, you give it to him, right? So at any point of time, when you are reach that particular set, you only assign those elements which are already not assigned to that particular guy, right? And so that it becomes a partition. Now, what is the property of this? The cost is going to be less than equal to whatever the cost of the sets were, and then you are done, right? So what we have learned is that, okay, but so it is definitely a set cover problem that I can treat it as, right? So if I put some metric here also, if I assume some other structural properties about this distance function, that will not change the property that it's a set cover instance. You understand my point? Because for any weight function this has this property. So in particular, for if the weight property has some metric properties, which we will come in a minute, this. So okay, so now what does this implies? This implies that if we could take this input and translate it completely into these instances, then this is nothing but I can run my set cover algorithm. It will give me order log client factor approximation, and I can take that solution, apply this modification, and give you an order log and factor approximation for my facility location. Okay. But the problem is that I cannot explicitly construct this set family because the set of family is very large. You understand my point? Okay. And that is what I told you, that you don't need to know. All you need in greedy algorithm, that at any point of time output me the set which is the most cost optimal. If I can give you an oracle for that, then you are done. Okay. I will not do this for this, but anyway I have to do this for metric, so I will do it there. Okay. So now you understand what sets I am talking about. Okay. Okay. So now I am going to give a greedy algorithm. I am going to define a charging scheme. Okay, and I am going to prove, oh, summation of charging scheme is nothing but summation of weight. That's the second thing I will show. Third thing I will say, okay, now let's look at the charges of a set, charges of a set and weight, how are they related to each other. Now remember, they write summation fz, this is where they get their fz, because for long I have imagined why are they coming up with this lemma statement, which I never understood. Okay. 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 So now I'm going to, so this will give you a log n factor approximation if we do not assume anything about D. But now I'm going to assume that D satisfies certain metric. Okay. Okay. So what is the meaning of D satisfies certain metric? So this is some client I, sorry, some facility I, this is I prime, J prime. Okay. Okay. So what I mean, basically metric always mean that direct distance is always shorter than what you call, when you take what you call like routes, right. So what I will mean that the green distance is going to be smaller than the, I first go to I to J prime to I prime to J, right. So the black path is always shorter than the direct path. This is basically what metric will mean. Okay? So, basically means that if you take a route detour, then you will always cost more. But if the cost functions were not defined this way, it doesn't mean, because I can have 55, 1, 1, 1, right. So, going is more expensive than doing the shortcut, doing the tour. So, this is not a metric, right. This is not the property of the metric. Property of metric is that this cost function should be in a way that detours are always more expensive than direct way. Okay. So, how will I translate this? This is what I will say is that distance from I to j is less than equal to distance from I to j prime plus distance from j prime to I prime, is that fine, plus distance from I prime to j. And this is true for all I prime in your facility and for all j prime in clients. Okay? Then this is what is called metric. Okay. Okay. Okay, so now let's try to construct an algorithm for this problem, and as we will go forward, we will see several interesting things. Okay. Okay. So always remember. So now I'm always going to take a set cover mental imagination of this problem. Okay. What I'm going to take a set cover imagination of this problem, which means if I think of a set cover imagination, then here it is, right. My U is set of clients. My family is what? My family is F I C prime I in my facility, C prime is a subset of C. Okay? And what is the weight of F I C prime is F I plus summation over j in C prime distance from I comma j, right. So, I have kept this intra. So, either you think of this problem or think of this problem, both are same for us, right. So, if in a nice way, if we can optimize this, then we can translate that as a solution to this problem. So, we can actually forget about facility location problem and just think about set cover, right. So, now this distance has a beautiful properties. Maybe in this set cover instance, by exploiting those beautiful set properties, right, we might be able to do much better. Okay? Okay. 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 When is Venkatesh class? 11:15 or 11:30? Why does it take? Okay, fine. Okay, doesn't matter. Still have half an hour. Okay. So now forget about facility location. Here is my set cover instance that I want to cover. Okay, but it is slightly different than set cover. So we will keep this perspective as well as this perspective. This perspective that okay, to utilize greediness, utilize the proof technique from set cover to this, but we will utilize this approach for other things. Okay. So what I mean by this? So think of this way. Here it is. Okay, and you are allowed to, and clients are located. These are clients are located. Okay, this is the client where the clients are located. Okay, and this is where potential facilities can be opened. Okay. Okay, these are the places potential facilities can open. Okay, but like not necessary that all will be open, but if it opens, you are allowed to make a green box around it. Okay, so the moment you open a green box, certain people will be served by that. You understand? Okay. Okay, so this is how the world looks like. Okay, but there are some heuristics that you must understand. That imagine that you all are served here at this point of time. So everybody, suppose there's only one supermarket in a city, what will you do? Everybody will go there. Or imagine that there's only one school in the city, then all the children will go to the same school, no? But so now imagine a situation that after 5 years, government decides that oh, it's too much. Let me open a new school here. What will happen then? Some people who were going before will start to go to the new place. You understand? Some people who were going before will start to go to the new place. Then what will happen? Because of that, what happens to my cost function? Do cost function increases or decreases? Right? Because set of people who will get reassigned here, set of people who will be reassigned here, so they were going too far now. Now the reduction will be, they were going say this, and now they are going this. So this minus this is my reduction, right? I was going this much, so green minus blue is my reduction. Okay, so that's another heuristic to think of this, right? That if new facility opens, it's possible that some people might be reassigned, relocated. Okay, that's very natural idea. Okay, that's okay. Okay, now, but how do I decide where to open my facility? That's the first question, and that is where I will apply set cover thing, right? Where to open this problem? So now when I look at from the facility location, then I have this picture, and then I have this idea of realignment. But now when I have to decide where to open a facility, okay, I will think like a set cover. Okay, so you understand? So like I will take both these and put them together during my heuristics. You understand? Right? Because what happens in set cover is that once I make a selection, I'm done, I have no choice. But here, if I open a new facility in the second iteration, some things might change. I have to be like, I have to think more like, what is that called? More like, this is something which is evolving, moving, right? So this is not that I just cover. I also think of this place like a homes and schools, right? If the locality has opened here, people will realign. So I had some cost. When I open new thing, of course cost will, but maybe some things will decrease, right? So it's very natural that if I think from the set cover perspective, so if you remember my set cover algorithm, what it was in the beginning, what it was trying to do. Please see what it was trying to do. If you just remember my set cover algorithm, so it was C. Okay, C is client here. Okay, so let me use. Please don't talk in the class. You have any question? Ask me. I will answer your question. Maybe your question is also important for other people. So just ask. Yes, of course.
How can we say that total cost will get reduced?
Imagine, it depends on the cost, no? Right? Imagine that going cost was far too much. For many people, it was going too much. Right? Now I open this.
Then that cost will increase. When opening a facility, that cost.
Of course, it will increase. Right? But imagine yourself that there are also a lot of people which are not covered, for example. Right? Imagine, I mean, like, okay. So look, the way my algorithm is going to work, right? It's not that, don't think it's a very realistic situation and try to mimic this, okay? It's just a covering objective with this, okay? It's just an intuition for you to develop what all possible ways can I moderate my heuristics, okay? But every time, how do I decide where to place, right? You are very right that maybe, the moment I pick up one guy, everybody is covered, maybe, but that's just a wrong way of doing it. Maybe the better way was to make 3 different places, and then their total cost is much better than picking up one, but I'm not precluding you. Try to understand. I'm not excluding that you just pick up one facility and everybody is mapped to that. I'm not excluding it. Am I excluding that here? Right? But maybe if I have 4 places I open, and then you have to also understand, right, the distances to people also is a part of my cost, right? So that will shrunk for too many people, that even if it is opening here is okay. You understand that they were paying so much money here that if I even after I pay this, like imagine that so many people are paying some taxi driver here. Now everybody can just walk, so that taxi driver is nothing, no? All I care about, if I sum the cost, it is okay to open here. I mean, you have to be realistic with respect to what you try to do. Okay? Okay. So what I'm going to say, okay, so we are going to maintain, what we are going to maintain, we are going to maintain some things. X subset of F, okay. These are the currently opened facility, okay. Okay. Currently opened facilities. Okay, currently opened facilities. Okay. D subset, set of covered clients. Okay. So when I decide to pick, maybe I will tell you which will be covered. Okay, and it also maintains sigma from D to X. Okay, not only I said which are facilities that are currently open, okay, which are the set of clients that are covered, and how are they covered. So sigma tells us how are they covered, like which facility covers them, right? So this is a function I have at any point of time. Okay. Okay. Is that fine? Okay. Now if I think from the just set cover perspective, what was my heuristic I would have applied? Because ultimately it's a covering problem, no? It's a covering problem. So what you would have applied? You would have said, hey, at any point of time, pick a set which is the most cost optimal, is right? So how will you write it? Okay. So at any point of time, what do we want to find? At any point of time, want to find a facility I, and Y subset of uncovered clients such that what is minimized? What is minimized? Tell me. Okay. Is that fine? This is what we did. Cost per set is minimized. Okay. So this is what normal greedy does, right? But as I told you, right, that imagine here is a world, looks like, and this is a set of D already covered, and some partition exists. This is what is given by sigma, right? Now what does this algorithm does is that, okay, let me cover some more people. So he decides to cover some people by opening a facility here, suppose, right? So this is the ith facility he opens, right? So definitely these people are going to be assigned to him, right? But now imagine that things which are here, maybe he would like to realign them, no? Maybe he would like to realign them to him. Before he was mapped to this because he did not know that this facility has opened. But now that this facility has opened, maybe, because what is the sigma function? Sigma function, if every client is assigned to nearest facility opened in X. This is the definition, no? Every nearest facility. But nearest was defined up until now with respect to opened facilities. Now if I open a new facility, it's possible that for lot of facilities, this is the nearest client, nearest facility, and I have to maintain this definition every time. So at every time I want to, what is the property of sigma? It maps a client to the nearest facility available in X, right? So what does sigma does? Because you understand, right, why sigma will assign to a nearest, because why do you want to you want to minimize the cost, no? So you always assign a client to nearest facility available in X, okay? That's first thing. So if I take new guy and assign this new set of guys, but then this, if I then notice that this sigma may not be even valid in this sense, because when I get a new, there may be some people for whom nearest has become this one, right? So if I just say no, make a new I, assign y to him, but now if you look at this newly partitioned black and a blue partition, this may not be the shortest. Imagine that, look at the set of elements covered and you are making some Voronoi diagram with respect to the shortest thing. Okay, is that right? Okay, fine. D will be always equal to, meaning?
Any set of facility will cover everything.
Yeah, but that may not be the most cost efficient way, no? Imagine that, like, you are so far that I don't even want to go there. I don't want education in my life. Okay, or there's only private school open.
So how will we decide D?
What is D?
What we have covered.
I have not told you the algorithm. I said at any point of time we will maintain the following invariant. In the beginning, what is X? Is equal to phi. What is D? Is equal to phi. And then I will tell you a procedure. What is a procedure? Imagine set cover algorithm. What you did? Among all the uncovered people, give me the set with a most cost efficient. That's a way to cover, no? I can run that algorithm anyway on this. It's just that is going to give me a log n factor approximation. I told you just now. Why will that not cover? You understood or not? What did I do? Let me run my set cover algorithm on this. It will cover everything in you, no? And that's your sets. Right? So I'm saying, what does a set cover algorithm would have done? Set cover algorithm would have done exactly this. At any point of time, you find a facility I. So if you want, I can say while D is not equal to C, we will do this, right? I can say after this, okay, want to find a facility, okay? Rather than want, I'll say find a facility I and a Y uncovered such that this happens. That's a cost efficient set. Then I'll say now what happens after this? D becomes D union Y. Go, right? And X becomes X union I. What's the problem in this? There's no problem. This algorithm will give you a log n factor approximation. Is that okay? Because I can also think of them as a set cover and just run the set cover algorithm. But if I translate the set cover algorithm, this is what it means, right? But as I told you, right? So if you look at this, at any point of time, if I can give you a polytime algorithm to find this, I'm happy, right? I'm happy. I don't need to know your whole set family for all that I know, right? If I can give you a polytime algorithm that it takes me, hey, which is an uncovered element? Oh, this is an uncovered element. Then it gives me a I and subset of client, which corresponding set is the most cost efficient. I'm done. Okay. But all I'm trying to tell you is that, so this is what we did, right? But if I look into the algorithm, there are something which we are not capturing, okay? And what am I not capturing is the fact that there are certain realignment can happen when a next facility is opened. How do we incorporate that into this? That is what I want to do. Okay. Okay. So I will do the same thing. Basically, this is the same algorithm, okay, but I will tell you. So this is the algorithm will be more or less exactly the same. Okay. Okay. So as I wrote, what it was, D was D union Y, and what else was, X was X union I. Okay. This is fine, but I want to do something more to my cost function. Okay. What is that something I should do here? I should subtract something, right? I should subtract what, right? Okay. This is what they do in the analysis, not in the algorithm. Okay. I put them into analysis. I put them into algorithm. Okay. Okay. So what I'm trying to tell now is the following. So I'm going to define a D function. Okay. So D is my currently. So I'm asking myself, if I open facility at I, okay, if we open facility at I, how much drop will I get, right? How much drop will I get? Okay, like what is the change? Okay, so I'm going to write change. If I open my facility at I and D are already selected clients, then let's see what their changes is. Okay. Okay, so I would like to be, what changes will happen? So before, the guy was assigned to whom? He was assigned to some other facility, and that was given by what? So if J is in D, he was assigned to sigma J, comma J, right? Minus D time I comma J, right? Is that fine? Is that okay? Okay, let me write it here. So what did you say? Sigma J, comma J minus, this is the cost which will change. I paid this much, now I am paying this much less. So D of I comma J. But maybe this J was already better off. This could be what? Positive quantity, no? So then he doesn't want to replace, no? He will only like to go if it is strictly less than 0. So then you put each of the guy is going to lose max of this. You understand? Some people already are at a good place, so why will they like to change? Because they are, if this is much larger quantity, then this is negative, right? Huh? Visible? In what sense?
I can't see it. Can you write it somewhere else?
Okay.
Mean of volumes.
Okay, wait. Max. Okay, so what I'm saying is, if I have an I, facility at I, okay, I'm asking if facility at I is opened, okay, how much drop of cost happens? This is what I want to understand, right? Because imagine that some client was going here, right? Now if he decides to go to the newly opened person, he was paying blue, he's paying black now. So how much is drop? Blue minus black. Is that fine? So this is what I'm trying to write. So this is what I'm writing here is delta of D comma I is equal to summation drop. It's just capturing the drop because you are anyway paying this much. Before you paid this much and say, hey, now return my money. So how much return money I will give you? How much return? Because you still have to pay this much, you know. So imagine that you paid 55 rupees and now the cost dropped to 35. How much will you ask me from? 20 rupees only, no? Because 35 you still have to pay to me, right? So that's all that I'm saying. That before, up until now, these people were paying some cost. But now imagine that the system says, for these people, cost has decreased, reduced by this much. That's it, right? So up until now, you have some cost locally. Now I made something, I said, but for these people, reduce the cost because that's the new system, right? So at any point of time, imagine that there's a system, there's a system which has some cost. And when system gets realigned, it has a new cost, right? So how do I cost the new cost? Newly paid plus subtraction of the people for which cost has decreased. That's it. So at every time, I'm trying to define a mechanism to come up with a new cost. So what I say, look at the D people, okay? Either they lose or they don't want to. So how do I capture that without worrying about this definition? I said, look at J in D, max of 0. I said, either you lose nothing because you are better off by that, or you lose. So this is why I write max. So I said, hey, before you were assigned to sigma j, and now I am going to be assigned to I comma j, right? So if this quantity is strictly greater than 0, then it will contribute. If this quantity is negative, meaning I better off where I was before, then this will contribute to 0. Then you don't drop anything from there. This, okay? So my new greedy heuristic should be about, at any point of time, if I decide to pick this facility, which all people's realignment will happen. So this is delta of D comma I. So if I choose a new facility and I decide to pick y number of covered elements, then I will pay opening cost of new elements, but I have to subtract realignment cost, right? Divided by, but it is paid only on these y elements. And that is very important, that you only paid here, okay? So this is my greedy heuristic, and we'll analyze this tomorrow morning 11:30 and show that this is a factor 2 approximation. Okay, so that's the whole idea. Okay, I'm done for the day.